start. First of all, good morning, everyone. My name is Arne Heitman. I'm from NVIDIA. And before I start with the presentation, I just want to share some thoughts, and I want to interact with you a bit. Don't be afraid. No one has to step up front on his or her own. Just a couple of questions, and just raise your hands if you think, yeah, that's true, or no, that's not true. Who of you knows NVIDIA? Oh, yeah, that's a surprise. Yeah, that's true. Who of you knows NVIDIA for gaming? I guess that's almost 100%. Who of you knows NVIDIA for, well, artificial intelligence and other things? Oh, that's... The camera is not filming you, but it's some people less. Who of you knows NVIDIA for networking? Yeah, from yesterday. Oh, that's fair enough. That's fair enough. At least you know us. And therefore, today I'm just here to talk a little bit about the other side of NVIDIA, not the gaming side, I'm afraid. So if everyone thinks, I was waiting for the gaming. Sorry, I don't want to disappoint you. But I'd like to tell you some things about the intelligent data center and what we think the intelligent data center is, and what we think drives the intelligent data center, and what challenges the data center today. When I was asked to do this presentation, I said, yeah, happy to do so. You hear from my accent, it's not Polish. I'm from Germany, so I came over from Hamburg, and I was very excited to be here after 3 years, a bit more than 3 years. I was really looking forward to it, and I thought, okay, yeah, talk about the intelligent data center of the future and the challenges and the opportunities. And then I thought, oh my God, what did you do? Because when I started with working on my presentation, I pretty soon found out a lot of opportunities we currently have in data centers, in the widest sense, are also challenges, and a lot of challenges are also opportunities, so therefore I mixed it up all. And I hope this is sort of, well, probably also entertaining, but gives you some insights and gives you some thoughts. Later on, if you have any questions around anything, you can reach out to me and the colleagues from ComSat and NVIDIA. We have our own booth in the booth section, and therefore just reach out to us. But what is driving the data center? What is really changing the mindset of the data center? We all know this, and I grew up in the same sense as some people in the room at least grew up in this sense. Data center was, well, transport data from A to B, from diverse applications running on a single server or something like this. There was no virtualization, there was no intelligence, it was just data A to B. For the networking and data at rest or data in motion, we didn't know these terms. We just knew data, and that was it. However, at latest, with the rise of AI and with the democratization of AI, we see that there is a shift in the mindset within the data centers. There is a shift in the skills that are needed. There is a shift in the technology that is needed. And it is probably the most powerful technology force we are currently seeing. Just remember 2 or 3 years back when I talked to people, and I have an engineering background, people said, well, AI, come on, it's just one of these buzzwords and no one cares for it. And then all of a sudden, the wave came along and it started. And you see, for example, what's happening when you use AI. We just had a question, how has NVIDIA contributed to the advancement of AI? You see the outcome over there? You see this was generated using NVIDIA NeMo services. And you see just a couple of things that are just needed and that are just shown in here for an intelligent interaction with a user. An intelligent interaction with a user means there must be some intelligence somewhere. And it's most likely not in the laptop over here. This is just the user interface, a dumb device. So today, with this development, the data center is sort of a canvas of this innovation. So it simply means that we have a range of opportunities, a range of new applications, new drivers, and we can use the data center to simply implement this and to make this becoming true. And of course, you need some things around this. A data center by itself is, well, cooling, power, some cabling, and then you need some switches. You need some CPUs for everything that's serial computation, for example. Oh, this doesn't work. Sorry. So we have some CPUs over there. We have the GPUs for parallel computation. And of course, you need the interconnects that help you. And an interconnect is not just a port as it used to be in the history. Now it is somewhat intelligent, provides offloading, provides security services, and so on and so forth. So why is it needed, and what's driving this, and what is enabling this? Let's have a look at this. So everything, literally everything that moves these days will be an autonomous machine. An autonomous machine simply means that it needs some sort of intelligence. And it's not intelligence like human intelligence, not that way, but a moving machine like that one, for example, over here, is very, very simple. The way that it has to detect that someone is in its way, it has to arrange exactly the same speed to let packages on the vehicle and not falling it down in the next curve, okay? And this is all to be measured, and this is all to be evaluated, and it's all to be predicted also. So therefore you need a lot of intelligence around it. You also need, excuse me, you also need a lot of intelligence for creating what we call, or what people call usually, the metaverse. In terms of the metaverse, we have something that is called the NVIDIA Omniverse. It is a platform that helps creating the metaverse. And metaverse in its widest sense sounds like, okay, it's again back to gaming, hooray, but not really. So what we do with Omniverse, for example, or what we can do with Omniverse, we can build digital twins. A digital twin of a factory, for example. A digital twin of a building. A digital twin probably of the Earth, or a digital twin of a data center. Just for planning, for proof of concepts, for example. Really for evaluating what is the most efficient way of building something like this. And the absolute driver, for now, is what we call large language models. Large language models go way beyond words. And think language not in terms of human language, like the words getting out of my mouth. It's probably also the genomes in our body. It is probably also chemical formulas. It's mathematics. All this is language. And these models are currently developing rapidly. So the modern data center is now not only the canvas we can use to create all these new things, it also becomes a sort of a factory, an AI factory. And it means that we do not only have a server somewhere, but we have a cluster of servers, a cluster of compute units within the network. And the compute units within our environment in the data center are, of course, in the traditional sense, the GPU. The GPU is a general purpose compute device, a general purpose serial compute device. Like, for example, we have now our NVIDIA Grace. Serial computing is really, really nice, and we all know this, and we are used to it since many, many years, and it works nicely, and we all know the more cores we put into a CPU, the more efficient, the faster we are. But if we really need something that's being done in parallel computing because we want to reduce the time to compute, and we can have an application that's parallel computing, then we accelerate computing with what we call a graphic processing unit, a GPU. So all parallel workloads like AI, like machine learning, for example, like video, so all workloads may become AI accelerated. So AI is not serial computing, not necessarily, but the driver really is parallel computing. And a lot of data centers these days do not necessarily use yet parallel computing, but we will see the trend, and the trend is already there. And it does not necessarily have to be a full data center right from the beginning, so don't get me wrong. But it is a way there, and it is a path there. Of course, when you have accelerated parallel computing and when you have serial computing, you need something that simply also takes some load from these processing units and simply outsources these processes, these applications, because they are very, very close to the network. Being close to the network means you need something that accelerates data-intensive tasks on its path, and this is what we call a data processing unit. Sounds strange. I also had to get used to a data processing unit as a term, because data processing for me is something which happens initially within a box. But network near tasks probably are also close to the network and can be processed by the network, hence the term processing unit. And this all has to be connected via a networking unit. We have NVIDIA networking. Now a final question, more or less a final question. Who of you knows from the past Mellanox? Aha, at least some people. Yes, Mellanox. So this is now NVIDIA networking. Straightforward. Same device is still there. Yes, please.
So, brilliant presentation, visionary. More important, you really have all the pieces, right, to make it happen. Can you zoom into the DPU piece? Because the rest is kind of obviously there. Right?
Yeah, we're going to the DPU. Yeah. And as you are the first one to ask, it's not a price. I need to have it back. That's the DPU. All right, so we need to provide an end-to-end connection, end-to-end connectivity overall with diverse switches, transceivers, network interface cards, or adapters as we call them, and of course more intelligent, more advanced devices. And the more advanced devices are called a DPU, and this is what we call a blue field DPU. It's now just passed around, just have a look at it. We removed the cooling body, so you can have a direct look at the DPU part, and the DPU part is a CPU, as a matter of fact, with some combinations, and you will see a nice die shot, and I will explain something around it. All right, now, some information, also some information which are more general, but this really shows you how important this topic now becomes, also within the network. First of all, a lot of people of you are using WhatsApp still, probably. And you can see over there how long it took for WhatsApp to have 100 million users. It is 49 months, a bit more than 4 years. For Instagram, it was almost half, just 26 months. Did any one of you ever try ChatGPT? Welcome to the club of the 100 million. It just took 2 months for ChatGPT to get 100 million users. Do you know what this means to the data center they are running? It is extending on an ongoing basis. So it's not just like, oh, we build a data center and then we have our task for the next 5 years. Everything is good. And then we have to probably upgrade the bandwidth, some new CPUs. Over here it is like almost on a monthly basis. They had to plug in new servers, new network. They had to offload a lot of things. And that's very interesting. The other driving factor really is the power limits we are facing. Everyone is talking about power consumption, especially in Germany. We had this discussion throughout the past winter. But this is what you see over here. The data center electricity usage is greater than 200 terawatts per year, which is 2% of the worldwide energy that is used. It doesn't sound much, but there is not 2% of the overall population running a data center. It's far less. And it will be by 2030 something like 5%. That's just the prediction. we are currently facing. So also over there, we need some things and we have challenges with some things. So first of all, from everything I told you until now, you can see that the scale and the performance of the data center capacities have to change. There is a need to change this. ChatGPT is one of the best examples. There is also a need to, well, let's say, make east-west traffic more efficient, to get down to the latency, or with the latency. You need an optimized network for this. You see that we have to be more efficient and more elastic, like over here. So the CPU burden and the resource provisioning have to be very, very elastic, because a lot of jobs, a lot of intelligence jobs, a lot of computational jobs are not long-term jobs anymore. They are short-term jobs, and they do not run on one single machine, they run on a cluster of machines. So every machine gets a fraction of this workload. And you need a secure and resilient infrastructure. We all have learned throughout the past that data centers might be attacked from inside and from outside. So we have to separate workloads. We have to securely separate workloads. And now, as promised, we are getting deeper into the DPU. No, we do. The smart NIC is in fact is a normal NIC with offloading. The DPU, what you see in here, where we first of all have an example of a traditional server. This is the traditional server. So we have a CPU with VMs and containers. Within that server, we have software-defined security, software-defined management. We have infrastructure management. We have the storage and the software-defined networking part. And it's all running within that single server on the CPU load, to the decrement of virtual machines, to the decrement of containers. You can use a smart NIC that has acceleration engines. These acceleration engines exist within the ASIC, so they are hard-coded, and you can do, for example, inline encryption. You can do some offloading for dedicated storage tasks. You can run RDMA, for example. All these things can run on a smart NIC. And this is a traditional NIC, more to say. So the goal of the DPU now is taking some load from the CPU in terms of outsourcing it. And what you do, or what we do, as a matter of fact, in a Bluefield DPU, we simply outsource all these management tasks. So that's what you efficiently do. How can you do it? Because you don't have an ASIC, you have a programmable CPU in terms and in place. So we offload things, we accelerate things, we also isolate workloads, and the CPU benefits from this because we have more CPU resources. And the CPU resources can be used for additional virtual machines, additional containers, additional workloads. And that's mainly it. So accelerated performance, we have a cloud scale efficiency, and we have a zero trust security. Well, zero trust security is more or less something like a nice buzzword we have. But implementing an efficient security. Just take a seat over here. And it is, and this is very important, it's fully programmable. The car that's just moving around looks efficiently like this. So the chip you see on the card itself is built with several different sections. One section is the ConnectX ASIC. So this is an interface, a network interface. On the card you have over here, which is a Bluefield 2 card, we have a ConnectX 6 network interface card. I think a lot of people of you know this, having this in servers, using this on a regular basis. You know the speeds and the feeds, and you know the capabilities, the smart capabilities of offloading. This is all within that chip. The next step, however, becomes much more interesting because then we have programmable ARM cores. So we have an ARM core infrastructure, and this is where we can run then, for example, the management, the offloading, where we can run some security, where we can run crypto key management, and so on and so forth. In addition to that, and this is all on this chip, we have 2 acceleration engines. These 2 acceleration engines can be used, for example, for deep packet inspection. So for regex, it's usable. And it's used by some of our partners already over there. You can accelerate storage like NVMe over fabrics. And finally, of course, what we need is some RAM, some memory, and an interface to the server infrastructure, of course, because we interact with some things within the server. And those are the PCIe golden fingers you have there. That's the physical thing around a DPU. Any questions around this? No?
I agree with you. I mean, the way you put the case is smart.
Yeah, exactly. Yes. I agree. I agree. All right. Now we are getting to the next step, because this is the hardware. And of course, as we have an ARM processor or a couple of ARM processors in there, we also need some software. Well, you know this, we build the platforms, we provide the platforms and the frameworks for all the developers in the world, for all the ecosystem partners in the world. And this is what we call Docker. So we currently have Docker version 2.0. Docker is the data center architecture on a chip. And this is a software framework for DPUs. And Docker, for those of you who work with GPUs already, some of you may know the term CUDA. And CUDA really is exactly the same, or when we just compare it, Docker is like CUDA for the GPUs. So we have a framework, and the framework enables a lot of different things. So we have support for enterprise, supercomputing, hyperscale applications. And you see it over here. We have some operations, we have security capabilities, networking, storage, all this can be done. And we have an ecosystem of diverse partners, like Canonical, like Juniper, for example, working with us, like Cisco working with us, VMware working with us, so a lot of partners working with us. And this is what you can get, and this is what you can do around this. So getting on with this, just giving you some use cases, and not all of those use cases we have I can present within the time remaining. So therefore, I just picked a couple of use cases really. And one of the use cases is delivering AI-ready infrastructures to enterprise data centers. Democratizing AI also means it's not for the supercompute clusters in the world, it's not for the rich enterprises in the world, but it is for all enterprises, and it is affordable, and that's very important. So with Dell, and also now with other OEM partners like Lenovo, for example, like HP, for example, we are working on a zero trust security for the VMware enterprise environments, and this is what you see over here. So with vSphere, we simply do the following. You see over here, we have the compute hypervisor and the applications running on it. Then we have a security isolation. And on the DPU, I keep this term just for the sake of the session, to be honest. We have outsourced the networking and security service, the infrastructure management, and therefore freed up resources. And that's the most important part of it. Freeing up resources means, and here are some examples, Nginx core savings, just with the blue field, and you see it over here. We have a web server with a stateful distributed firewall, and have, without this 8 cores. Using a DPU, we reduce this to 0, which means we free up 8 cores. Well, if you have one server, you say 8 cores. Well, that's not much. If you have 10 servers, it's already 80 cores. If you have 100 servers, it's 800 cores. Just carry on with the maths. And therefore, you see that it really, really reduces the footprint. It's not only that you save resources for the CPUs, which can be used otherwise, but it also saves then energy around this. Another example, sorry, that was German. Straight. Another example you see over here with vSphere Distributed Services Engine. Redis in-memory value, you see there are 36 Redis streams, and it goes down from 12 to 0 cores. That's simply it. And the throughput also goes up dramatically. Therefore, you gain a lot with it.
So I got lost. Is it Sony or is it Redis?
This one was Redis.
Redis.
Yes. All right. We can also accelerate firewalls, and it is a very, very similar concept as with VMware. Okay, so the traditional server has all the firewalls, all the IPsec next generation firewall, and so on inside, and we simply outsource it to the DPU cores and let the work being done there. And again, the outcome is less cores being used. If you don't want to go into the, well, let's say, depth of security, if you say, oh yeah, I have my firewalls, I have my firewalling concept, everything is good. Another way you could do with a Bluefield DPU is you just accelerate your cloud network. Cloud network is not like the hyperscalers or something like this. A lot of organizations these days run networks in a cloud-ish manner. Even conservative organizations start thinking about, oh no, we are not going to the traditional approach with core distribution access. We are going to some leaf spine technologies. We are working with overlay networking and so on and so forth. Well, working with overlay networking, working with tunneling protocols simply means that we might offload this load from the networking edge directly to the server, which means on the Bluefield DPU, we are running a networking operating system, which we call host-based networking. And host-based networking gives you the capability of outsourcing, for example, or ending your VXLAN tunnels directly at the server edge, which still is part of the network then. And then comes the NIC part and the server part. So you have a programmable way to extend your network reach. You have line speed networking, you have line speed encryption, and you also have line speed visibility with the management tools you can use. So networking in general now moves more and more to the cloud model, which means these days we have software-driven automation. We don't configure on the console anymore. This is how I learned it many, many years ago, and I was just proud of all my certificates, and it was great having all these certificates. They all expired, because we all work with automation right now. We don't need these certificates anymore, really. We're changing into CI/CD, so it's not like the traditional approach, implementing something, letting it run for 5 years, hopefully, fingers crossed, or doing a lot of troubleshooting. We work with microservices and microsegments, and we also need new skills. That said, we don't need the ones who sit in front of the console in the middle of the night because they have change requests and they have the maintenance window at 2 o'clock in the morning. But we can do something on the run, probably, hopefully, because we tested it before and we have other skills in this environment. So therefore, we have new applications challenging the data centers, AI-based applications, network near applications. We have an increased demand for distributed apps, for storage, for multi-cloud environments. Completely different from what we saw just 5 years ago even. We have CPU capacities being consumed by infrastructure near services. They have to be outsourced somewhere. And east-west traffic massively increased. I'll just give you one example from a customer I'm currently working on a project with is fairly simple. So the access to his network, so north-south access, is just 25 gigabit. Fair enough for everyone. And it's a couple of thousand users in there. But the east-west traffic demands currently around 400 gigabit per second. Just for the east-west traffic. That's the amount of data just being distributed within the network. This also drives us from building less complex networks. In the past, and some of you might remember this, we had to learn so many protocols. Just a couple of those protocols over here. See it like PIM, like RIP, OSPF, EIGRP, I learned it by heart. IGMP, PRVRST, LoopGuard, all these spanning tree protocols. Who of you does still remember spanning tree? It's a handful of people, yeah. Right, and what did we have to monitor and troubleshoot all this? Command line interfaces, SNMP, SPAN, CDP, not much. So it was tough. I did my own troubleshooting certifications at that time. It took me a week just to learn troubleshooting, and it was not the end of the learning curve at that time. Throughout the time, it became less and less, and these days we have far more means to monitor and predict what's happening in a data center and in the network, and we just need less protocols. Of course, this is something like a dramatic view of it. Not all data centers are just running with BGP and EVPN, but more and more data centers are running on that. So therefore, you need something that's not fairly intelligent from the base, which can learn the intelligence inside, and which is more or less what I would say composable. So composable means the hardware you use should be something where you just can implement the network operating system as well as the applications that you need at the very moment. And if you have a change in the future, just implement a new, well, let's say Docker container, or just implement a new application. Just manage this as a server operating system. So from the closed mainframe-like locked boxes we have with high switch prices, with a lock-in of the customer to a specific vendor, we're moving over to open networking, where you can choose the hardware, where you can also choose the hardware on purpose. You need probably more powerful devices close to your AI infrastructure than you need it close to, well, let's say the standard servers. You probably need very, very intelligent devices at the edge where you need security and other things. So therefore, use the hardware, use the software you need, and try to avoid the licenses. That's probably the best you can do. We all know this term, pay as you grow, or pay as you need. The best always is just pay once and then use a box. So therefore, having a box with diverse operating systems that can be used over there, like the NVIDIA Mellanox Spectrum switches. You can also see those at our booth, at the ComSet booth. You can run Cumulus Linux on it, which is Linux, or you can go for Sonic, for example, but you can also run, if you want to try it, native Linux on it. Just for the sake really of the session and to demo to what openness really means, this is what you see over here. One example you can run is what we call pure Sonic. Other people call it community Sonic. So therefore, that's the open source Sonic operating system. Another question I know. Who of you knows Sonic or ever heard of Sonic so far? Yeah. So what is it? It's a network operating system invented, created by Microsoft. There is a word of mouth that Microsoft thought about bringing in something like Windows, but then they went for a Linux-based operating system for their Azure cloud, for their Azure cloud stack. And they just told everyone, look, if you want to work with us, you have to support this operating system. It's free. Use it, implement it on your boxes, and then you can work with our cloud stack. That's simply it. then you are supported. And it becomes more and more popular. At the very moment, the community is mainly driving it in terms of really cloud implementations, but it's getting broader acceptance. So all this sounds very nice. So we have a lot of hardware, we have a lot of software, and the main question really is, well, should I start everything at once? No, you don't have to start everything at once. So what you can do is you can simply build a digital twin. It sounds massive. So the original digital twin, for example, with NVIDIA Omniverse, can give you a whole factory, if you wish to. But we also use the simulation, for example, in NVIDIA Drive Sim. Autonomous car driving is something that's currently becoming more and more popular. It is also something that's becoming more and more discussed in a lot of different discussions, political, ethical, technology-wise. But it is also a sort of a simulation and a learning process. This is all AI you have in there. And if your car, for example, identifies the next space for parking and shows it in your display, this is also sort of artificial intelligence and a learning process. In data centers, you can also build your own model, and this model is called NVIDIA Air. NVIDIA Air is for free. You can register, and then you can implement and test something. You could also simulate your own data center over there. So if you want to simplify a deployment, if you want to go into a testing phase, and a lot of people just don't change, you just don't waste all your resources within the data center and just say, okay, I don't need it anymore, I'll just buy something new, ideally NVIDIA, ideally via Comset, sorry for this advert. Then you first of all test it. And you can test it with two things. One is Launchpad. And Launchpad itself is an application where you can identify how and which AI can be used to accelerate your compute. You can test it with Launchpad. If you want to go for the networking, you can use NVIDIA Air and simulate and deploy the environment. All right, and finally, before I come to an end, this really has become true with Omniverse. We are building something which is called the Earth 2 initiative. So we build a large compute cluster with partners, of course not on our own, but it will be a digital twin of the Earth, which is used for an ethical reason, because the AI data center of the future can also be used to do scientific research in terms of what can we do against the climate change. How can we save at least some parts of the world? And with that, I'll leave it open for some questions, and I do thank you.